Recent observations have revealed two significant anomalies concerning the interstellar object 3I, Atlas, now under scrutiny by multiple space agencies. The first anomaly was a photometric shift indicating a measurable alteration in the object's brightness pattern. This suggests either variations on its surface or a change in how it reflects sunlight. Shortly thereafter, NASA confirmed signs of non-gravitational acceleration. This means 3I Atlas is moving in a manner not fully explicable by gravity alone. A trajectory update was promptly issued, and while the deviation is minor, it is substantial enough to significantly alter future projections. At present, the data does not point to a definitive cause, yet it also fails to align with the established natural models. Space has often been described as a realm of predictable rhythms with celestial bodies tracing elliptical paths governed by gravity. However, for 3I Atlas, that rhythm has faltered. NASA's Jet Propulsion Laboratory has officially confirmed that this interstellar visitor is no longer adhering to its predicted trajectory. Its path, once smooth, calculated, and obedient to cosmic laws, has subtly shifted. This deviation, though measured in mere fractions of a degree, represents a profound departure in cosmic terms. One might envision the control room screens at JPL softly aglow in the darkness, where thin lines representing trajectories suddenly show a disturbing bend like an errant pulse. A single new coordinate, a recalibration, and abruptly our solar system hosts a visitor that refuses to conform to its mapped course. The numbers themselves do not alarm. Instead, they quietly reveal a pattern, disrupting a long-held cosmic symmetry. This critical update emerged during a period of government shutdown when most official channels were dormant. Nevertheless, Daniel Adams, one of NASA's dedicated orbital analysts, proceeded to upload the corrected data. Perhaps he understood that in the realm of science, silence can sometimes be more impactful than immediate disclosure. Previous orbital charts depicted a standard inbound curve from interstellar space, a swing around the Sun, and an exit towards the outer darkness. The revised path, however, drifting by only a few arc minutes, points to an unaccounted for force, a push beyond the mere influence of sunlight or cosmic dust. Imagine sketching a perfect ellipse on a blackboard, only for a single chalk line to abruptly veer off. This subtle yet defiant divergence is all it takes for the known to unexpectedly lead into the unknown. Across the globe, from ground-based observatories in Hawaii to deep space monitors orbiting Earth instruments, registered this anomaly with a quiet disbelief. Data from SOHO Stereo A and Geo19 unequivocally confirmed the deviation. Even after meticulously accounting for error margins, the mathematics held firm. This object is accelerating without any discernible source of propulsion. Picture a bullet gliding through thick molasses that suddenly lurches forward as if remembering an unfinished journey. A celestial trajectory is not expected to exhibit intent yet. I-Atlas behaves as though it does. In the intricate field of orbital mechanics, such a shift would typically necessitate a new vector of force, perhaps from outgassing a collision or magnetic drag. However, none of these phenomena have been observed, at least not yet. At this precise juncture, the narrative of 3I Atlas transitions from mere prediction to an unfolding presence. The fundamental question now hangs suspended between humanity and the distant stars. If gravity alone did not move it, what did? Our Sun was expected to be its undoing. At approximately 126 million miles, or about 1 1/3 times the Earth's distance from the Sun, I-Atlas reached its perihelion, the closest point in its path around our star. For the majority of comets, this moment marks a period of dramatic transformation or even disintegration. Ice's vaporized dust erupts and their nuclei often fracture under the intense fury of solar radiation. They typically flare brightly, then fade, their bodies gradually dissolving into the solar wind. Yet 3I Atlas defied this expectation. It emerged from that inferno virtually intact. Its core did not disintegrate and its coma did not thin. The predictive models indicated its collapse, yet instrument readings consistently showed its persistence. 3I Atlas journeyed through the Sun's scorching domain, an environment where temperatures soar high enough to strip iron from meteorites, emerging almost entirely unchanged. Visualize a dark nucleus smoothly navigating through vast curtains of plasma, each photon striking its surface with the force of a hammer of light. If one could stand beside it shielded from the Sun's lethal brilliance, they would witness the solar corona streaming around it like liquid gold, the comet miraculously holding itself together against the very physics designed to tear it apart. Scientists at SOHO and Stereo are meticulously observed awaiting the characteristic signal of rapid brightness decay, the spectral signature of disintegration. This signal never materialized. The telemetry remained steadfast. Even at its closest approach, when the comet's surface temperature should have climbed to hundreds of degrees Fahrenheit, the object resisted evaporation. This raises a profound question for planetary science. What composition allows a body to survive such proximity to a star? Ordinary water ice and even dense clathrates of carbon dioxide and ammonia would have quickly vaporized. The composition inferred from its reflectivity suggests the presence of tougher, more refractory compounds, possibly metallic silicates, or perhaps something entirely unknown to current science. Its albedo, a measure of reflectivity, changed only slightly, while its physical shape remained remarkably stable. At its distance of approximately 126 million miles, sunlight strikes with about 2/3 the intensity that relentlessly scorches Mercury. Imagine enduring an environment akin to standing beneath 1,000 suns, each one a mirror of fire. This is the crucible 3I Atlas traversed. Yet when instruments reacquired it days later, its brightness had not diminished. Remarkably, it had increased. Such an outcome challenges conventional understanding, prompting scientists to label it as unexplained. Some astronomers hypothesize a denser, perhaps carbonized crust effectively sealing internal volatiles beneath its surface. Others ponder if centrifugal stresses were uniquely counterbalanced by some deeper inherent cohesion, a structure capable of redistributing heat rather than succumbing to it. Whatever the underlying mechanism, 3I Atlas profoundly defied the fundamental expectations, breaking one of the solar system's quiet commandments. Everything that approaches the sun must either bow or burn. It did neither. Instead, it continued its journey shimmering blue-green within the solar wind. Upon receiving the initial images, scientists anticipated the familiar emerald hue, a green glow typically indicative of carbon molecules excited by sunlight, a spectral hallmark of every conventional comet. However, the hue began to shift subtly at first, then decisively. 3I. Atlas started to emit a distinct blue light. This was not the faint shimmer of ionized gas, nor the turquoise haze associated with diatomic carbon. It was a deeper, more intense tone closer to the incandescent blue of a welding arc, hotter, sharper, and seemingly deliberate. This colour was so brilliant that instruments aboard the Hubble Space Telescope required recalibration of their filters to prevent saturation. From a distance, it appeared as though the comet had somehow transcended the thermal logic of its class. In physics, blue light signifies higher energy, higher frequency, and shorter wavelength, typically correlating with greater heat. Yet the core of 3I Atlas, still hundreds of millions of miles from the Sun, should have been far too cold to emit such vibrant blue. Picture observing this through the lens of SOHO, the Sun's overwhelming glare inundating the detector, every pixel struggling for balance. Amidst this visual static, a singular streak of electric blue cuts sharply across the frame. Such a colour is generally not expected in the vastness of space, where the cosmos predominantly favours the reds and ambers, the long, tired wavelengths of cooling dust. Blue in this context felt like a declaration of intent. One could almost perceive the photons on their skin as if sharpened and tuned to pierce the darkness with enhanced efficiency. What could possibly orchestrate such precision in a naturally occurring object? While gas emissions from carbon monoxide or ammonia can account for specific fragments of the spectrum, they cannot explain the sustained radiance observed for weeks. It was as though the light itself had decided to shift its register, announcing a new distinct identity. Some astronomers initially attributed it to optical interference, a mere trick of scattering under the intense solar glare. However, interference typically fades. This glow persisted. Others proposed a chemical transition suggesting unknown compounds awakening under the bombardment of ultraviolet radiation. Yet the available data did not neatly support these explanations. Thus, we find ourselves observing an object that undergoes a colour transformation without a corresponding change in temperature, a phenomenon behaving as if light itself is choosing its form. When viewed not through the rigid lens of equations, but with open perception, one witnesses something serene yet profoundly disobedient, a blue pulse orbiting a yellow star, introducing a new accent into the cosmic vocabulary. This is a shift that not only challenges our measurements, but also our very perception. As our senses strive to adapt and the human eye attempts to comprehend the next phase of this unfolding mystery, commences. Its brightness intensifies, its spectrum deepens, and the inquiry expands beyond colour, now encompassing motion. Whatever turned blue is now beginning to accelerate. Light is fundamentally chemistry expressed as rhythm. Every wavelength represents a reaction at a continuous dialogue between energy and matter. When sensors were focused on 3i Atlas, this dialogue refused to adhere to the established grammar of nature. The initial data presented textbook-perfect emission bands of carbon monoxide, carbon dioxide, and ammonia, the common molecules activated by ultraviolet sunlight. Under normal conditions, these gases fluoresce in the blue-green range, typically between 420 and 480 nanometers, producing a modest, soft, and temporary glow that quickly fades. Yet this glow from 3i Atlas did not fade. Even as solar radiation waned with increasing distance, the vibrant blue remained steady and unbroken for weeks. Telescopes recorded emission lines that consistently refused to decline, and the ratio of short to long wavelengths held constant. For scientists, this persistence was profoundly unsettling. Energy is expected to disperse and molecules should cool. Instead, 3i Atlas behaved as if its act of glowing was self-sustaining. Initially, analysts hypothesized a dense atmosphere of trapped gas, a chemical cocoon. However, pressure readings modeled from the comet's coma expansion rates rendered this explanation impossible. The observed outgassing was minimal, yet the intense light persisted. This leads to a critical question: what mechanism allows cold material to radiate with the temperature of flame? The object's apparent color temperature was approximately 7,000 Kelvin, higher than the sun's surface despite its actual thermal temperature being perhaps 300 Kelvin, around 82 degrees Fahrenheit at best. A body colder than boiling water shining with the radiant hue of blue steel. This stark contradiction compelled a deeper investigation. Hubble's spectrographs revealed not a random scatter of light but narrow structured peaks with almost harmonic intervals between them. Some researchers describe this as a coherence pattern, a form of resonance manifesting within the molecular bonds themselves. Others suggested crystalline silicates or metallic grains reflecting ultraviolet light with constructive interference amplifying the brightness, much like a mirror precisely tuned to a single frequency. In simpler terms, imagine light encountering a surface so exquisitely precise that instead of merely reflecting it, vibrates each photon, causing it to multiply the next. The surface effectively transforms into a type of optical drum. The dust around 3i Atlas is not simply scattering sunlight, it is actively shaping it. However, one crucial element remains unmeasured: the ultimate source of this excitation. What sustains this unique blue radiation? Known chemical processes cannot maintain such emission for weeks without continuous replenishment. Perhaps the answer lies beneath the surface in buried reservoirs releasing volatile gases through narrow fissures, or in electromagnetic induction triggered by solar wind currents. Or perhaps this phenomenon is something entirely different, a form of photonic memory, where light continues the gesture of its arrival. When science encounters such persistent anomalies, language often falters. We may label it fluorescent reflection or resonance, but each term offers only a partial truth. Could the blue light not be a mere product but a fundamental state of being, where light actively chooses a way to remain visible? In scientific equations, heat signifies movement atoms, trembling photons escaping. Yet sometimes movement transcends mere physics to become profound meaning. When astronomers observed 3i Atlas, they witnessed heat behaving paradoxically. The comet should have been freezing its core temperature even at perihelion, hovering near the limits of deep cryogenic ice. Yet the light it produced implied an energy output far exceeding its thermal state, a cold body shining like a star. The numbers clashed, but the image remained consistent, temperature and brightness diverging as if one belonged to the realm of physics and the other to an unstated intention. Pause and let this contradiction settle. Imagine holding an ember that emits no warmth, only light a flame you could touch without burning. This is what the data describes. Some scientists refer to this as apparent temperature, a perceptual illusion stemming from specific wavelengths dominating the emission. Others cautiously speculate about energy coherence. Where light becomes highly ordered, its heat concealed within structure rather than diffused as chaos. Regardless of the explanation, this phenomenon suggests something profound, that heat is not merely a quantifiable number, but potentially a form of will, the inherent effort of matter to express energy without sacrificing its form. When we stand under the sun, warmth is a direct message from radiation to our flesh. For 3i Atlas, warmth transforms into a negotiation between cosmic distance and the imperative of survival. It cannot burn, it must endure. And endurance on such a cosmic scale approaches a form of consciousness. Telescopes record this simply as reflectivity. But what if reflectivity itself is resistance, a refusal to allow energy to pass untransformed? The blue radiance of 3i Atlas might be the visible consequence of that defiance, heat reorganized into light entropy folded back into order. If so, the comet is not simply radiating power, it is actively redirecting it. The sun provides heat and the object returns coherence. In this profound exchange lies a symmetry. Energy arrives chaotically and departs with the precision of a thought. Imagine the cosmos replete with such responses, minute negotiations where matter answers radiation with elegance instead of surrender. This would imply that the universe is not merely a chain of accidents, but an ongoing conversation, each particle capable of deciding how to receive its fire. This is not poetic embellishment of physics. It is the recognition that energy itself might possess a preference. Perhaps this is what we are witnessing in 3i Atlas, the first subtle hint that even heat can exhibit a form of agency, choosing visibility over destruction. As the brightness grows steadier, and the spectrum narrows from that serene blue surface, something else begins to change. Not temperature, but momentum. The subsequent measurements will no longer focus on colour, they will illuminate motion. Newton's first law of motion dictates that an object in motion will stay in motion unless acted upon by an external force. But what if the acting force is imperceptible? In the meticulously kept records of NASA's Jet Propulsion Laboratory, a new entry quietly appeared almost without fanfare. The file for 3i Atlas was updated with two seemingly minor figures, 84 miles per day squared and 37 miles per day squared. To most, these are mere increments. To the field of orbital mechanics, they represent a profound defiance. The larger figure signifies radial acceleration, a consistent push away from the sun, as if something beneath the comet's surface were continuously releasing momentum. The second, a transverse component, indicates a sideways drift, an unexpected nudge across its plane of motion. Together, these components form a trajectory pattern that gravity alone cannot explain. If one were to chart its current orbit, it would appear to bow outward, the curve trembling like a string under an unseen tension. A path that once faithfully obeyed the sun's gravitational pull now quivers under another influence, silent yet persistently reshaping its course. At this cosmic scale, such sustained acceleration appears impossible for a natural object. A comet, unlike a spacecraft, possesses no thrusters, no fuel, no engine to ignite. Yet the measurements are unequivocal. Observations from the major planet center, the Hubble Space Telescope and ground stations across Chile and Hawaii, all converge on the same precise deviation. To contextualize this, an acceleration of 84 miles per day squared means that every 24 hours the object gains an additional speed equivalent to approximately 5 feet per second every second. This seemingly small increment is sufficient to alter its long-range trajectory by millions of miles over just a few weeks. For a nucleus only a few miles wide, such sustained energy output fundamentally defies known chemistry. Typical comets such as 19P Borrelly 67P, Churyumov-Gerasimenko or Comet Ison exhibit non-gravitational effects less than 1/100th of this magnitude. Even during their most violent eruptions near the Sun, their thrust is generally gentle, chaotic, and diffused through multiple jets of gas. What is observed from 3i Atlas is neither chaotic nor diffused, it is remarkably clean and deliberate. Picture a small body gliding through the solar wind, streaming blue light while its motion consistently diverges from prediction. The mathematical models struggle to keep pace. Every update to its orbital parameters renders the previous one obsolete, as if the object is rewriting its own ephemeris in real time. In celestial mechanics, we rely on established cause and effect relationships, radiation pressure, outgassing, thermal recoil. Here, however, known causes fail to suffice. The momentum curve of 3i Atlas reveals a continuous directed change, showing no signs of random venting or rotational bias. It accelerates as though under deliberate guidance. Scientists, while seeking to remain restrained in their language, find that the data demands explanation. They categorize it as non-gravitational acceleration, a term that subtly conceals a profound unease beneath its precise scientific veneer. It is a phrase employed when equations cannot fully explain a motion, yet the desire to sound calm persists. We can discern the inherent hesitation within this term. The pause between numbers, the unspoken recognition that this is not mere noise. Something is exerting a push, but nothing visible appears to be moving. When Daniel Adams released the updated trajectory during the NASA shutdown, he provided no commentary, only precise coordinates. Perhaps this silence was intentional, leaving ample space for interpretation. Now, across multiple databases, the consensus is firm. The deviation is both real and persistent. The comet's outbound path no longer aligns with solar models. The farther it travels, the stronger this divergence becomes, almost as if the acceleration feeds on distance itself. In the vast arithmetic of orbits, this represents a faint whisper of intent, a motion that sustains itself beyond conventional explanation. The numbers, though initially seeming small, have spoken, and what they declare is both simple and impossible. Something out there is moving by choice. Every orbit contains a singular moment of immense power, the perihelion, the instant when a celestial body passes closest to its star. It is the cosmic throat of gravity, where velocity peaks and the gravitational pull is strongest. For centuries, celestial mechanics regarded this point as sacred and immutable. However, 3I Atlas appeared to treat it as an opportune moment. At approximately 126 million miles from the Sun, the comet executed its most significant change. Instrument readings unequivocally showed that the shift in its trajectory, its unexplained acceleration, commenced precisely at perihelion, not before, not after. This exact timing suggested a deliberate choice. If one were to model this as a maneuver, it represented perfect timing to escape a gravitational well. The most efficient burn or thrust occurs at the very bottom, at the point of highest efficiency, where every ounce of thrust yields the maximum change in velocity. This is precisely what spacecraft execute during a gravitational slingshot maneuver. But comets are not supposed to understand orbital mechanics. The data curve distinctly shows a sudden radial push at perihelion. The 84 miles per day squared increase in acceleration began precisely when the Sun's intense radiation should have been tearing the object apart. Instead, it seemingly harnessed that pressure. The equations read like a pilot's log of a meticulously executed burn at a moment of maximum stress, a precision rarely observed in nature. If one could safely stand nearby within that field of radiation, they would witness the Sun's glare engulfing the nucleus like liquid fire. Then an infinitesimally small change in its glow, a subtle realignment of vectors, and the path bends outward, a subtle yet absolute act of control. Hubble images, taken both before and after perihelion, confirm this. The dust coma remained stable, showing no explosive jets or signs of mass ejection that could account for the observed momentum. The comet's tail did not fragment. Instead, it rotated. The motion appears less like a chaotic plume of gas and more like a precise orientation adjustment. In orbital terms, this is akin to pressing the accelerator inside a whirlpool. Any other natural body would spiral inward, consumed by gravity's relentless demand. 3I Atlas, however, chose the exact instant to push outward, converting its gravitational descent into an escape trajectory. This level of precision leads to a question that few scientists are comfortable with. Conventional models relish can randomness orchestrate strategy, while thermal recoil can cause drift and sublimation can generate thrust. The observed synchronization. The alignment of peak energy with peak resistance strongly implies calculation. Mathematical models attempted to reframe this as a mere coincidence, a momentary instability in the thermal gradient or a fortunate release of pressure. Yet when simulations were run, none could accurately reproduce the observed effect. The timing had to be exact within a window of hours. Nature as we understand it typically operates not on hours of precise timing, but on processes of erosion, gradual change, and slow surrender. One can sense what the data in its raw form cannot explicitly state. The comet moved as though acutely aware of its cosmic context, as though it patiently waited for the perfect moment to act. After perihelion, the object's acceleration gradually began to taper, settling into a new outbound course. Crucially, its trajectory never reverted to its predicted line. It had definitively broken free. In the quiet interpretation of those numbers, a profound question persists. If one truly wished to depart from a star, this would be the quintessential method. And so 3I Atlas continues its outward journey, shining with an improbable blue, unhurried and persistent. Deep within the complex tapestry of observational data, A remarkable moment emerged where light and motion began to resonate with each other, a point where brightness ceased to be merely a reflection of energy and instead appeared to become it. After its perihelion passage, telescopes noted an extraordinary phenomenon. The vibrant blue hue of 3I Atlas did not diminish as it receded from the Sun. On the contrary, it intensified. Its spectrum tightened and its emission lines grew sharper and more saturated, as if frequency and force had decided to move in perfect synchronicity. When plotted, the curves representing luminosity and acceleration, though distinct measurements, rose and fell together precisely in phase. Brightness was no longer a mere byproduct of motion. It was its inseparable companion. Comparing timestamps revealed an almost perfect alignment. The peak of blue emission coincided precisely with the onset of the 84 miles per day squared radial acceleration. It was as if colour itself had transformed into propulsion, as if light had become a form of ignition. Spectrometers aboard the Hubble Space Telescope SOHO and several Earth-based observatories independently confirmed this startling observation. At the exact moment the comet began to accelerate, its spectral lines subtly shifted towards shorter, deeper blue, higher energy wavelengths. And as the acceleration stabilized, so too did its distinctive color. It was as if the object had ignited itself. One can visualize the Sun's immense glare as a vast ocean of pressure, with every photon acting as a wave pressing inward. Now imagine something within the comet not collapsing under this pressure, but resonating with it, converting that incoming light into outward momentum, a luminous recoil. The human eye would simply perceive a breathtaking cobalt flame traversing the darkness of space. But the underlying numbers reveal a more profound symmetry. Each increase in brightness corresponded to an identical increase in outward thrust. This was not a random flare nor a chaotic event, but a harmonious, synchronized response. Theoretical models falter at this juncture. Outgassing the conventional explanation for cometary thrust cannot account for such precise correlation. Random jets would scatter light, not synchronize it, and dust release would typically redden the light. Yet the data demonstrates an optical coherence rarely seen even in meticulously controlled laboratory lasers. Stepping back from the intricate mathematics, one might interpret this in simpler terms. 3. I-Atlas was converting light directly into motion, an energy exchange so remarkably clean it resembled deliberate intention. Some researchers cautiously labelled it coincidence, others perhaps more provocatively termed it art. The observational graphs, however, depict a choreographed performance, a pulse of colour transforming into a pulse of movement, each feeding the other in perfect unwavering balance. At this point, speculation naturally drifted towards metaphor, suggesting the comet had fired its engines. Not engines of combustion, but engines of pure radiance, where light ceases to be a mere consequence and becomes the active cause. In this profound sense, ignition was not a metaphor at all. It was a literal ignition of photons, an awakening of order within the chaotic reflection of sunlight. The blue grew deeper, denser, still almost metallic in its intense hue. The coma shimmered with coherence, not noise. Observers began to refer to it as mirror light, a glow that seemed intrinsically aware of its direction. And through this luminous mirror, a singular truth quietly shimmered. If motion can organize light, then light too can organize motion. This ignition was not a mere flare, it was a profound declaration. Something it seemed had learned to actively push back against the sun. The stream of observational data eventually tapered off, but the indelible impression remained a glowing blue ember in the deep darkness, still accelerating as if the vacuum of space itself had learned to remember momentum. The fundamental rule of celestial mechanics dictates that when motion changes, everything previously charted must be rewritten. A single deviation can cause the entire cosmic map to collapse. The ignition of light by 3I Atlas left behind a bewildering trail of mathematics. Observatories worldwide found their data feeds inundated with numbers that no longer fit established models. By late October, the orbital models of 3I Atlas had diverged so significantly that the Minor Planet Center, NASA's JPL, and ESA's Solar Dynamics Office each produced separate and differing predictions for its future path. None of them agreed. This is the inevitable outcome when acceleration refuses to decay as expected. The resulting curves and graphs of velocity over time began to climb steadily instead of levelling off. What should have been a gentle arc towards escape transformed into an expansive hand reaching outward into the utter unknown. For the modelers, this necessitated a continuous cycle of recalibration. Every few days, its ephemerides, the tables of its predicted positions were rewritten. Observation calendars shifted and telescopes were repeatedly retargeted. The comforting rhythm of certainty had completely disintegrated. Imagine a table of scientists poring over projections, each attempting to predict the comet's position. Just a week into the future, their new plots diverging like the myriad branches of a river delta. The initial difference, a few arc seconds, rapidly expanded to millions of miles when extrapolated over longer distances. On a cosmic scale, a millimetre of miscalculation at the source can manifest as a continent of error downstream. This was not merely an error, it was a fundamental incompatibility. The models designed for ordinary comets, which assumed sublimation solar pressure and random jet activity, simply could not account for the unwavering consistency of this thrust. 3I. Atlas accelerated as though under continuous precise control, not in chaotic bursts. The pattern was smooth, elegant, and unerringly exact. To accommodate this, new terms had to be introduced into the equation's coefficients for sustained impulse directional bias and temporal coherence. The comforting familiarity of established equations began to mutate. When software engineers reran the dynamics, some simulations catastrophically failed due to floating point overflow, indicating acceleration beyond all expected limits. It was not the universe misbehaving, it was the limits of our expectations being exceeded. This recalibration rippled outward. Observation schedules at Pan-STARRS, Subaru, the Hubble Space Telescope, and the James Webb Space Telescope, JWST, all had to be rewritten. Orbit tracking artificial intelligences had to rebuild their entire learning sets. For a brief period of days, 3I Atlas was technically unplottable. Its projected future lay entirely outside the tolerance of any existing model. If one were to trace its path on a sky map today, the new line would no longer gently curve away from the sun. Instead, it would distinctly rise, bending against gravity's expected pull, a signature that appears less like a predefined path and more like an active decision. In that subtle, defiant bend lies the quiet collapse of an entire era of understanding. For centuries, motion was equated with obedience, gravity pulling, and matter yielding. Now, one small object suggests that movement itself might contain memory, that trajectories might not merely follow laws, but actively respond to them. This is the profound consequence, not danger, not collision, but a fundamental correction to our understanding. Every law of motion now implicitly carries an asterisk, unless the mover actively participates. The recalculated charts now display a faint new branch, an outbound arc that departs the solar system at a steeper angle than ever before, carrying with it the persistent residue of blue light. The data labels it escape. The silence surrounding it whispers choice. From that singular departure, another kind of gravity begins to exert its pull, the irresistible weight of questions too profound to ignore. In the rigorous world of science, silence often conceals itself behind the innocuous phrase, awaiting review. Yet there are moments when the silence itself is the review. On October 2, 2017, the high-rise camera aboard NASA's Mars Reconnaissance Orbiter captured a series of high-resolution images of 3I Atlas as it traversed the inner solar system. Each frame, nearly 30 megapixels in detail, was sharp enough to discern surface features on an object only a few miles across. If these images had been released, they could have revealed intricate geological gradients, perhaps even fracture lines where light interacted with the comet's surface. However, those frames never surfaced. No raw FITS files, no public catalogue entry, no archival index exists. The imaging request is recorded in logs and the data packet was confirmed as received. Yet what the camera saw remains unseen. One can visualize the scene, a spacecraft meticulously orbiting Mars, its advanced optics briefly pointed sunward. Photons streaming across nearly 126 million miles converge onto a sensor smaller than a fingernail. The exposure lasts only a fraction of a second. Then the data feed goes dark, sealed away in telemetry storage. Those precious bits of light still reside somewhere folded into NASA's internal archives, tagged and patiently awaiting. Why are they withheld? Officially, the agency cited data prioritization. Informally, researchers whispered that the images revealed more than anticipated, perhaps a brightness anomaly or a specular reflection inconsistent with rough ice or dust. This is speculation certainly, but it is speculation fueled and sustained by an unsettling absence. If released, those frames could simultaneously answer several critical questions. Was the blue emission localized or uniformly distributed? Did the nucleus exhibit vents or a discernible symmetry? Was there any evidence of structured geometry planes, edges or patterns? The high-rise optics boast a resolution of nearly 1 foot per pixel at optimal distance. Even accounting for the immense separation each pixel from that observation could have covered over 160 feet of the comet's surface, ample resolution to detect distinct regions or directional textures. For planetary science, such detail represents an extraordinary level of intimacy. In a field where transparency is paramount to trust, the absence of this data becomes an ethical quandary. Science is fundamentally built upon the principle of open release, on the idea that seeing is a collective endeavour. When an image is withheld, it does not simply vanish, it multiplies endlessly within the imagination. Perhaps the unspoken concern was the risk of misinterpretation, a glint mistakenly identified as symmetry, a shadow misinterpreted as deliberate design, or perhaps it was a measure of caution, a temporary pause until a scientific consensus could form. Yet true consensus necessitates universal sight. We are therefore left with a profound irony. The most powerful camera ever dispatched to another planet may have captured the clearest view of an interstellar visitor, and no one is permitted to see it. Somewhere within a server on Earth, an untouched frame silently awaits its timestamp frozen in metadata. What it specifically contains becomes secondary. What its absence generates is primary. The unshared image has evolved into an object of fascination in its own right, a photograph that exists only as rumour. In the vast night of information, that withheld picture glows more brightly than any publicly released one. And as the silence endures, the orbit of doubt begins a drift not of planets but of fundamental scientific principles. Among the many enigmas posed by 3i Atlas, none disrupts our understanding of cometary geometry as profoundly as the phenomenon of its forward jet. By definition, comets trail dust ions and vapour, all of which are dragged backward by the relentless solar wind. Their tails invariably point away from the sun, never towards it. However, when the Hubble Space Telescope captured a series of images employing polarized three-dimensional mapping, something extraordinary occurred. This established orientation appeared to reverse. Instead of the familiar fan of ejected material stretching behind a bright distinct vector extended ahead of the comet's motion, a luminous taper pointing forward. Initially, analysts suspected a projection error, a rotational anomaly in the observation angle, or a simple coincidence of camera orientation. But the datasets were meticulously precise. Multiple exposures captured across 90 minutes, corrected for parallax using starfield references. The jet remained firmly anchored to the sun-facing side, unwavering in its forward direction. To ensure the veracity of these images, they were reprocessed using independent systems at ESA's Space Telescope Science Institute. Researchers reconstructed the coma's three-dimensional density with advanced volumetric algorithms. The result was unequivocal: a concentrated emission extending consistently along the direction of travel, approximately 8 degrees off the nucleus vector, remaining stowell across all frames. Such a geometric configuration cannot be explained by tail inversion or solar perspective alone. A comet's tail follows radiation pressure. This jet, however, appeared to lead with purpose. One might envision a small object gliding through the vacuum, shedding light not as a trailing wake, but as a guiding beam, an arrow of emission actively anticipating its path. If conventional rules applied, the momentum flux from such a jet should logically slow the nucleus. Instead, its thrust vector precisely matched the observed acceleration, exhibiting an aligned, efficient and continuous propulsion. Here, physics appears to fold back on itself. For a force to point forward, it must be actively driven rather than passively dragged. Sublimation vents typically eject mass backward, generating recoil. A forward jet would necessitate a reverse gradient, a region of sublimation that pulls instead of pushes, an impossibility under passive thermodynamics. The simplest test involved angular inversion. Could the apparent direction simply be an optical illusion? In simulations, even extreme perspective shifts could not reproduce the precise alignment observed in Hubble's data. A comet's tail cannot appear ahead of it unless its material velocity somehow exceeds its own orbital velocity, unless the dust is moving faster than the comet itself. The spectrographic data introduced yet another layer of complexity. Emission lines from the jet perfectly matched those of the nucleus, with no Doppler shift indicating backward motion. This was not debris passively leaving the comet, it was light actively leading it. Some researchers termed this optical entrainment, a coupling between radiation and ejected plasma that produces a stable standing column of light. Others argued for electrostatic columnation, magnetic sheath actively shaping plasma into a narrow forward beam. Both explanations, however, struggled to maintain coherence over extended periods. Yet this forward jet persisted for weeks. Its luminosity even pulsed in near synchrony with the comet's rotation period and optical heartbeat precisely timed to its spin. One might pause here contemplating this profound symmetry of the absurd, a comet that glows where it should dissipate and accelerates where it should naturally slow. This image fundamentally defies the very grammar of orbital mechanics. Perhaps this is not emission in the conventional sense, but rather orientation made visible, a luminous trace of how the object actively determines its direction. In the grand lexicon of the solar system, every object traditionally bends before the solar wind and radiation pressure. Plasma, flow, the sun's endless exhalation all shape every tail, every orbit, every trace of dust. The direction of that wind is universally understood as law, but 3i Atlas did not bow. When the forward jet initially appeared, physicists meticulously rechecked their models of solar wind dynamics, hoping to find a flaw in their interpretation. They found none. According to all known mechanics, an object of its size exposed to such intense radiation should have been relentlessly pushed backward, its charged particles stripped and drawn into a trailing plume. Instead, its light pushed forward into the current. The simulations were relentless in their confirmation. Each code run assumed a standard flux from the sun-solar radiation pressure at its distance, which is potent enough to sweep micron-sized dust downstream at hundreds of miles per second. Yet the Hubble data, independently confirmed by SOHO and PAN-STARRS, clearly showed an emission columnated against that flow narrow, steady, and aimed directly into the oncoming plasma. Imagine standing in the face of a hurricane and observing a candle flame leaning into the wind. That is precisely what the numbers describe. To reconcile this, some proposed a shield effect, hypothesizing that the nucleus's magnetic field might have defected the local solar wind, thereby creating a quiet zone where light could orient freely. However, field strength measurements offered no such protection. A comet of that mass, primarily composed of volatile ice and dust, cannot sustain a magnetosphere of any significant scale. Others invoked electrostatic tension, an invisible web of charged grains interacting with sunlight to create an apparent forward beam. Yet the spectral consistency, with its blue emission locked in phase with the acceleration, strongly suggested direct energy transfer, not mere reflection. The contradiction deepened a luminous jet maintaining its coherence directly against the prevailing wind direction. Solar physicists rigorously tested new boundary conditions. Could a rotation vector combine with outgassing to produce a transient forward illusion? The answer consistently came back negative. Even at maximum rotational speed, the material's velocity would still trail the sun's formidable force. Nature as we comprehend it simply does not generate thrust against its dwarfs. And yet here was the irrefutable proof: image, spectrum and motion all aligned in defiant contradiction. One can almost sense the hesitation in the published abstracts. The language becomes carefully conditional, perhaps, possibly it may indicate. But between those carefully hedged verbs, another truth implicitly breathes: the object appears to understand the flow and actively chooses resistance. It is as if 3i Atlas treats the solar wind not as an obstacle to be overcome, but as a partner, absorbing its push, converting it and folding it back into its own propulsion. The very wind that typically tears comets apart paradoxically becomes the medium of its coherence. This is a recurring motif, an echo of intention heat that remembers motion that responds, and now wind that yields to opposition. The contradiction is no longer solely between theory and observation, it has become one between passive submission and deliberate design. In the deep analysis logs, a phrase began to appear quietly: technological signature. The phrase technological signature that appeared in analysis logs is not an announcement nor a firm conclusion. Rather, it represents a profound hesitation embedded within the language of science. The observed acceleration of 3i Atlas, its distinct light curve and its phase-locked blue emission, all align with a precision rarely sustained by natural systems. The remarkable coherence between its brightness and momentum remains a scientific enigma. It is this unusual convergence of precise behaviours that compelled the use of the term signature. The data itself does not explicitly claim design, it simply rejects randomness. Every recorded pattern reiterates thrust peaking precisely at perihelion color stabilizing at maximum energy output, and its trajectory consistently departing from gravitational symmetry. These are not mere declarations of purpose, but consistent records of an unexplained phenomenon. For many, the notion of technology within the context of comets seems superfluous. Physics, when extended to its limits, can often mimic intelligence. Radiation can drive order, and geometry can appear deliberate. Yet in the case of 3I Atlas, the observed efficiency far exceeds conventional expectations. Models based on sublimation and recoil fall short by margins too significant to disregard. In comparative simulations, typical outgassing processes cannot sustain acceleration for more than a few weeks. 3I Atlas has maintained it for months. Dust emission should typically redden a comet's colour. Instead, it's blue deepened. Random fractures would usually disrupt alignment. Here they seem to reinforce it. Some researchers attribute this to an extraordinary coincidence, a convergence of extreme conditions that create the illusion of control. Others argue that such convergence is the very definition of control. Within published reports, the language subtly shifts inward with phrases like active modulation and directed impulse replacing older terms such as jet behavior. These are not metaphors, but rather attempts to describe observations without prematurely assuming their underlying cause. There is no definitive proof of a mechanism, no visible machinery, no measurable field beyond known chemistry, yet the effect persists light and motion meticulously organized with striking economy. If technology is defined as efficiency expressed through matter, then 3I Atlas performs as though it intrinsically understands this principle even if it lacks conscious intention. If coincidence implies multiple systems aligning without an inherent cause, then 3I Atlas behaves as though coincidence itself has learned rhythm. One can meticulously examine every dataset without definitively choosing either interpretation. In one view, the comet is a masterpiece of natural tuning, a celestial body that somehow discovered stability at the very edge of chaos. In the other, it stands as a quiet artifact, continuing a function long after its original context has vanished. Neither perspective breaks the observational data, both remain provisional, and in the expansive space between these two views, astronomy finds itself confronting its own reflection, the delicate limit where meticulous observation touches the boundless realm of imagination. The term technological signature remains in the archive unconfirmed and undisturbed. No one unequivocally labels it as evidence, yet no one dares to delete it. It simply waits much like the unshared high-rise frame its presence made luminous by its very absence. Whether a coincidence of natural forces or a construct of unknown origin, the pattern holds firm, a motion too stable, a colour too precise, a silence too deliberate. And in that unsettling stability lies a quiet bridge to what comes next, a transition from interpreting numbers to patient waiting from mechanics, to deeper observation from light that acts to light that endures. In astronomy, transparency is a ritual as ancient as the discipline itself. Every photon meticulously collected, every coordinate precisely logged, is meant to be openly shared with the world, measurable, reproducible and accessible. The night sky belongs to no one, and therefore to everyone. Yet in the unfolding record of 3I Atlas, this sacred chain of openness falters. The highest resolution image ever captured of the object, the high-rise frame from the Mars Reconnaissance Orbiter on October 2, 2017, remains conspicuously absent from every public database. Telemetry logs confirm the downlink of the frame was completed, verified data packets were received. Then the sequence ends. No raw file, no preview, no confirmation of failure, only a quiet, inexplicable gap. High-rise emission, renowned for its unwavering data transparency, has no precedent for such an enduring silence. Every observation of Mars, every meteor track, every calibration target follows a standardized sequence compression indexing and release to the planetary data system within 90 days. Billions of pixels flow seamlessly from orbit to archive with this singular exception. In JPL's official catalogue, the entry for the image still bears a passive label, status pending verification, a phrase so procedural yet it effectively freezes the image in a bureaucratic limbo. Behind the firewalls, the frame undeniably exists, outside them only metadata. The reason for its withholding is not a lack of storage or bandwidth, both of which are abundant. It is rooted in a culture of caution, an ingrained institutional instinct to verify meticulously before revealing. To protect the integrity of data, they inadvertently delay public access to site. And in that delay, something profound shifts. Transparency morphs into tension. light. Once a universal symbol of openness and enlightenment is recast as something restricted, something to be earned, one can trace echoes of this pattern throughout historical archives. The Voyager infrared maps of Uranus held back for months. The Galileo dust impact spectra paused for calibration the Hubble servicing mission. 4 images that lingered unprocessed while systems were rebooted. Each instance was justified at the time, yet each is now remembered as a moment of institutional hesitation etched into history. What makes the 3i Atlas image uniquely different is the sheer scale of its context. This is a body from another star observed perhaps only once and potentially never again. Its light travelled across interstellar distances, a journey of 43,000 years to reach that sensor. Yet that vital signal is halted at a bureaucratic threshold, a gate erected by policy, not by physical limitation. This is not a conspiracy, it is a consequence. When institutions control access to light, they also inevitably shape its narrative. An unseen image transforms into a burgeoning question, and questions proliferate far faster than data can ever be released. Some scientists contend that premature release risks widespread misinterpretation. Others counter that secrecy breeds the very distortions it aims to prevent. Between these opposing views lies the enduring paradox of knowledge. To prove truth, one must first permit its visibility. Imagine standing beneath the night sky, fully aware that a pristine frame exists, a perfect capture stored on Earth, yet unseen by any human eyes. It is simultaneously there and not there, present and withheld like a photon, momentarily trapped within its own reflection. The locked archive is not merely an absence, it is an active deed. It defines what the world is allowed to know and precisely when. It teaches that even in a universe seemingly built on openness, silence carries immense weight. Perhaps the frame contains nothing unusual, only dust noise, a faint ambiguous trace of blue. Or perhaps it harbours something that defies immediate interpretation. Either way, the pause itself becomes compelling evidence of how institutions often move far slower than the speed of light. In astronomy, every discovery commences with an act of exposure. Light reaches us uninvited and impartial, and we collectively agree to bear witness to it. This fundamental agreement between the sky and the observer forms the quiet core of scientific endeavour. But sometimes light arrives and is intentionally not shared. Sometimes the act of seeing transforms into the act of keeping. The withheld frame of 3i Atlas has transcended its technical absence to become a reflection of something deeper, the tenuous border between knowledge and control. For in the grand cosmic order, nothing truly belongs to us. Every photon traversing the void is older than our species, older than memory itself. Yet we have learned to classify it, to decide precisely when it is seen and by whom. Light once symbolized liberation, a beacon of revelation of reason, marking humanity's long climb from ignorance into patterned understanding. But what transpires when that very light becomes restricted, when its release hinges upon institutional permission rather than boundless wonder? Astronomy at its core is a moral language subtly disguised as mathematics. Its equations speak eloquently of energy, distance and time, yet beneath these precise measurements lies a constant, profound question: who truly gets to know? When the high-rise image of 3i Atlas was locked within an archive, the subsequent silence resonated more loudly than any data ever could have. It was the palpable sound of hesitation, the uneasy space between discovery and trust. Scientists may call it protocol, philosophers might call it the loss of faith. There is an inherent ethical gravity to every observation. When data is concealed, curiosity bends around it much as starlight bends around massive objects. The result is a distortion not of the sky, but of meaning itself, because when light is withheld, it does not disappear, it becomes a shadow. Imagine the bitter irony: a beam of interstellar illumination travelling for 43,000 years, untouched by cosmic dust or gravitational influence, finally reaching a sensor orbiting Mars only to be halted inside a human firewall. Not lost to the immutable laws of physics, but intentionally paused by human caution. The ethics of light do not demand recklessness. They demand humility to release what we see, not because it is perfect, but simply because it exists. Because transparency is not just a methodology, it is the sole means by which knowledge can truly remain alive. Throughout the history of scientific observation, this tension has consistently replayed itself. When Galileo first meticulously charted the moons of Jupiter, his peers accused him of heresy. When Hubble's observations revealed the expansion of the universe, it was met with widespread disbelief. Each act of revelation carries the same inherent risk to show is to challenge, to publish, is to relinquish control, and yet light persistently insists. It travels at a constant velocity, indifferent to political manoeuvring, to fear, or to delay. It never requests to be curated, it simply arrives. What we choose to do with it ultimately defines us. Perhaps the profound lesson of 3i Atlas is not solely about the comet itself, but about our own reflection in its missing image. When illumination is held back, it ceases to be true illumination. When it is shared even imperfectly, it fulfills its intrinsic nature once more. Silence in science is never merely emptiness. It is a profound medium, transparent, heavy, and full of its own gravity. Where light gives us direction, silence ultimately grants us depth. When the image of 3i Atlas failed to appear, it did not erase curiosity, it multiplied it. Questions arose like static onto dead frequency. Astronomers began comparing timestamps, correlating tracking data, and matching exposure logs from other telescopes that might have observed the same region. Every gap invited another calculation. Every absence demanded reconstruction. In physics, absence is not a void, but a field. When something disappears, the equations must still balance. So the scientific community began to fill the missing term, not with certainty, but with motion. For many, the silence became more intriguing than any image ever could have been. It hinted at contradiction, a perfect dataset captured and stored yet unseen, an experiment half complete, its conclusion withheld. The pause was not natural, it was procedural, and in that pause inquiry found its next trajectory. One can imagine the sounds of that moment, keyboards striking in the night, emails flowing across observatories, questions are replacing announcements. Science had encountered its own echo. Silence does not kill knowledge, it roots it. It compels curiosity to change its orbit, to bend around what cannot yet be known. It creates new paths of approach, new hypotheses, new attempts to see from another angle. Just as gravity shapes light, silence shapes attention. After the high-rise archive closed, a second wave of observation commenced. Institutions meticulously prepared instruments for December 19th, the date when 3i Atlas was predicted to reappear from behind the Sun. It would pass 269 million kilometers, approximately 167 million miles from Earth, far enough to challenge every lens, but close enough to test every theory. A coordinated plan quickly formed. The Hubble Space Telescope, the James Webb Space Telescope, and ground-based optical arrays would synchronize their observations. This was no longer solely a mission of discovery, it had become a rigorous test of transparency itself. Silence had inadvertently dictated a new schedule. The data teams termed it open verification, a deliberate attempt to replace secrecy with synchronization, transforming patient waiting into a collective act of clarity. Where one telescope might pause, another would continue. Where one record was missing, another would speak. The universe, after all, offers no ultimate silence. Even the cosmic void hums with background radiation, a faint whisper from the very beginning of time. What we perceive as emptiness is often merely a slower, more subtle form of signal. Perhaps this represents the unspoken discipline of science to learn how to listen, even when there appears to be nothing left to hear. For in silence, meaning travels differently, not as brightness, but as persistence. The locked high-rise frame of 3i Atlas, once an absence, now acts as a gravitational centre for all further inquiry. Its missing image has garnered more attention than any published photograph ever could. It transformed, withholding into momentum. And so as December approached, every telescope on Earth prepared to observe again, not because silence was broken, but because silence itself had become the compelling reason to look deeper. On December 19th, the geometry of observation reopened. For the first time in months, the trajectory of 3i Atlas cleared the Sun's disk and re-entered measurable space. The object stood at a distance of 269 million kilometers, 167 million miles from Earth beyond the orbit of Mars, yet within the reach of precise instruments. Observation plans for the Hubble Space Telescope and the James Webb Space Telescope were meticulously synchronized with a network of ground observatories in Chile, Hawaii, and the Canary Islands. The configuration was timed to the second, with phase angle, heliocentric distance, and solar elongation arranged into a narrow interval of visibility that would last only hours before orbital drift once again obscured the view. This was not merely an event, but a precise configuration of ratios, alignments, temperatures, and reflection space momentarily arranged into possibility. At Hubble's focal plane, imaging sensors prepared for a target magnitude of 9, faint for the unaided eye, but clear for the mirror. Infrared detectors on the James Webb Space Telescope stabilize near 250 Kelvin, approximately -9 degrees Fahrenheit, maintaining a steady background for the incoming spectrum. On the ground, optical arrays were calibrated to meticulously compensate for atmospheric turbulence and Earth's rotation. Guiding systems rehearsed the same slow corrections they would apply once photons arrived. In the precise language of orbital mechanics, such intervals are known as return windows, brief geometric alignments where the line of sight between the Sun-Earth and the observed object becomes unobstructed. To miss this interval means alignment dissolves into years of waiting. To capture it means the data forms a continuous thread across time. Patience itself becomes a scientific method here. Waiting is quantified and exposure time and repetition becomes the instrument that refines uncertainty. Pointing coordinates were articulated verbally, rather than through symbols. Right ascension 5 hours 11 minutes, declination plus 24 degrees. The light travel delay was approximately 15 minutes, the time a train of photons would need to traverse the vast gap and reach the detectors. Curiosity at this scale becomes almost a physical sensation. Every measurement is a question phrased in units of light. Every return is a partial answer. 3i. Atlas was moving outward on a hyperbolic path at a speed exceeding 42 kilometers per second over 26 miles per second, faster than the escape velocity of the solar system. It was leaving, not orbiting. The December observation window therefore served two purposes simultaneously: a final verification of earlier measurements and a poignant farewell to proximity. The instruments did not merely record motion, they recorded flux, reflectance, polarization, and angular deviation. Each line of data meticulously translated motion into comprehension. Through those numbers spoken aloud, magnitude 9.5 minutes of light travel time plus 24 degrees of declination, the earlier silence surrounding the object began to resolve. What silence conceals observation, ultimately restores. This window was less about a dramatic revelation and more about continuity, the rigorous discipline of returning to what had previously vanished. As Earth rotated beneath aligned observatories and as the James Webb Space Telescope steadied at the Sun-Earth Lagrange point, two light from 3i Atlas arrived once more. Not brighter, not nearer, but demonstrably measurable, repeatable and real. If the behaviour of 3i Atlas were entirely natural, then conventional physics would still provide sufficient explanations. There would be no need for hidden engines, no anomalies defying explanation, no concealed design, only the expected interplay of ice dust heat and the long, predictable arithmetic of sublimation. This is the fundamental premise known among astronomers as the natural hypothesis, that the strange acceleration and brilliant blue light of 3i Atlas can be fully explained by the known chemistry of a comet reacting to sunlight. By this reasoning, the object should have lost a substantial and measurable portion of its own body. At perihelion, its closest point to the sun temperatures would have surged beyond 300 Kelvin 80 degrees Fahrenheit, more than enough to vaporize surface ices. Carbon monoxide, carbon dioxide, and trace amounts of ammonia would have erupted into the vacuum, forming a broad cloud of gas and dust. If such a process had indeed occurred, then the numbers lead to a clear and unavoidable conclusion: approximately 10% of its total mass must have been lost to produce the observed acceleration. 10% of a nucleus estimated at 30 billion tons translates to a staggering subtraction of 3 billion tons over just half a year. That immense mass loss, if real, would undeniably leave a visible signature even from Earth. It would manifest as a dense asymmetric coma, expanding for millions of miles and a tail of reflected sunlight bright enough to scatter through instrument filters. The James Webb Space Telescope, observing in infrared, would definitively detect carbon dioxide emissions at wavelengths near 4.3 microns. The Hubble Space Telescope, tuned to the visible band, would register a faint brownish-red halo typical of heated dust grains. Ground-based spectrographs would capture the same unmistakable fingerprint in optical spectra: bright emission lines of cyanogen and carbon monoxide alongside traces of organic molecules shattering under solar radiation. This is precisely what the natural hypothesis predicts: a comet dramatically shedding mass, glowing intensely from within, leaving its history behind as an expansive trail of vapor and particles. However, such predicted beauty also carries a burden of evidence. The mathematics are strict. To sustain the measured acceleration of 84 miles per day, squared in the radial direction, the outgassing must achieve velocities of hundreds of feet per second. Jets erupting continuously, their force far greater than anything observed from ordinary comets. The surface would have to fracture repeatedly, exposing vast reservoirs of volatile ices, with each new vent expanding as sunlight deepened the melt. This process should be inherently chaotic, brilliantly luminous and utterly unmistakable. If this were true, the telescopes would be recording it now. The December observation should have shown a wide, diffuse envelope of dust, its brightness declining exponentially as the material dispersed. The coma would be visible even through thin cloud cover, with the gas spectrum dominating the data streams. In this predicted view, 3I Atlas remains a comet rare certainly, but still obedient to the Sun's established pattern. Its colour would be a mere byproduct of photochemical excitation, its acceleration a simple reflex of melting, and its silence nothing more than the elegant simplicity of physics performing its immutable work. Yet even as these predictions are articulated, they carry an undertone of persistent uncertainty. Nature explains much, but not necessarily all. To truly prove itself, the sky must respond with irrefutable consistency, dust, light, spectra, and the precise geometry of mass loss. If the comet is indeed natural, this pattern will undeniably emerge. If not, the very absence of evidence will speak volumes. Every scientific hypothesis must inherently contain its own potential undoing, a clear, specific line where evidence, if absent, unequivocally breaks the model. For 3I Atlas, that critical line is composed of dust and light. If the natural explanation is correct, then telescopes must see what the physics demands: a vast coma of vaporized ice, a faint red glow of scattering dust, and a trail of debris expanding outward as the nucleus erodes. If this is not seen, the hypothesis fails. This is the precise path of refutation, the test embedded within the claim itself. It requires no belief, only rigorous measurement. When the James Webb Space Telescope meticulously turned its mirror toward the returning object, its infrared detectors intently searched for carbon dioxide emission lines near 4.3 microns. Hubble simultaneously scanned the visible spectrum, tracking for the brownish hue typical of silicate dust. Ground observatories swept through polarization filters, attempting to precisely separate gas emission from mere reflection. Each system operated in parallel, tracing the brightness curve hour by hour. But the expected cloud was conspicuously absent. There was no broad coma, no expanding dust veil, no plume consistent with heavy mass loss. Instead, the object remained remarkably compact, its brightness stable and its colour still a profound deep blue. Even the faintest scattering that should have followed sublimation was nowhere to be found. In the lexicon of scientific observation, an absence is an active result. It means the assumed mechanisms, melting, venting, and acceleration by gas pressure, are simply not operating at observable scales. The comet, if it is a comet, does not behave like one. Mathematics further deepens this contradiction. To explain the recorded acceleration without a corresponding loss of dust, one must invoke thrust without exhaust motion, without reaction. This is not forbidden by physics, but it belongs to an entirely different category of phenomena, not cometary but potentially engineered. The astronomer Avi Loeb had articulated this months earlier. Non-gravitational acceleration without visible outgassing implies an internal energy source. This statement, simple and almost clinical, carries an immense weight of possibility. Within that phrase, internal energy source, the boundaries between what is considered natural and what is artificial begin to deceive. For some, the silence of the spectra, the lack of expected emissions, is sufficient proof. For others, it is still too early to draw definitive conclusions. Yet within the data, the absence persistently repeats itself. No dust tails, no carbon monoxide bands, no decay in brightness over weeks of continuous monitoring. A comet that does not fade is by definition no comet at all. If these readings persist, the entire established model of natural cometary behaviour collapses. The path of scientific revision then leads not to a mere mystery, but to a fundamental re-evaluation. New hypotheses must emerge concerning the object's structure, its propulsion mechanisms, and its ultimate purpose. Every scientific discipline experiences such pivotal moments when observation squarely contradicts comfortable assumptions. When the expected pattern refuses to appear, in that very refusal lies the engine that drives knowledge forward. Observation begins long before light ever reaches a sensor. It commences in the human mind, where we consciously decide what seeing truly means. Before the December 19th alignment, as telescopes patiently awaited photons from 3I Atlas, another form of preparation unfolded, a profound ritual not of instruments, but of human perception. in the cutting-edge laboratories of NASA, in the bustling control rooms of the European Southern Observatory, and in the quiet, dedicated corners of university observatories, scientists discussed less about raw data and more about mental posture, how to observe without predetermined expectations, how to measure without inherent presumptions. This is because every act of measurement implicitly contains an act of faith, the belief that what is observed will fundamentally correspond to what is real. To adequately prepare the gaze is to loosen that faith just enough, allowing surprise and the unexpected to penetrate. The night before the critical observation, many scientists performed small personal gestures of readiness. Some meticulously rechecked alignment sequences, reviewing exposure logs for the 100th time. Some sat in profound silence, watching live telemetry streaming from satellites orbiting at the Lagrange point 2, a celestial point of gravitational balance between Earth and the Sun. Others simply looked upward, without a telescope or filter, gently reminding themselves that the boundless sky is infinitely older than any intricate instrument they held. In a profound sense, this is the most ancient practice in all of astronomy, the delicate balance between focused attention and deep humility. Machines may capture photons, but it is only human awareness that transforms them into meaning, and meaning in its deepest form demands stillness. One can visualize this collective pause, screens softly glowing in dimly lit rooms, the quiet hum of air conditioners, the faint static of radio receivers warming up. Across the entire planet, observatories in Hawaii, Chile, the Canary Islands, and South Africa were meticulously synchronized to a single overarching purpose, not to rigidly prove a predefined theory, but to remain utterly open to whatever might appear. The human gaze is not a passive receptor, it actively shapes its object. Too much expectation distorts, too little focus dissolves. So they adjusted themselves with the same meticulous care with which they adjusted their optical instruments, breathing evenly, grounding their thoughts, aligning their attention with boundless patience. In the philosophy of observation, this is sometimes referred to as the discipline of waiting. It is the profound recognition that the act of seeing is in itself an integral part of the data. For light does not simply arrive, it is received. And reception fundamentally depends on readiness. As the critical minute approached, the world's instruments achieved a state of perfect equilibrium. The James Webb Space Telescope stabilized at its cryogenic operating temperature. Hubble's gyroscopes locked precisely on target. Ground-based mirrors became utterly still under the crisp night air. Each sophisticated system in its own intricate way mirrored. The human state quiet, expectant, perfectly balanced. For a fleeting moment, science resembled meditation. The sky and its observers formed a single unbroken circuit energy, departing a distant object traversing 167 million miles, entering metal glass silicon, and ultimately human consciousness. To prepare the gaze is to remember this unbroken chain that every photon carries not just information but direct contact. That looking into the vastness of space is also in a profound way a means of being seen. The December observation was not merely an experiment. It was a moment of profound alignment between technology and awareness, between the insistent question and the resonant silence. And in that precise alignment, the gaze became truly ready. We have gazed outward for so long that we may have forgotten how easily the universe gazes back. Every observation is a mirror, quiet, exact, and infinitely patient. Light travels for centuries, crosses tumultuous magnetic storms, swirling dust clouds and vast planetary shadows, only to arrive at a polished mirror on Earth, where it transforms into a question about who is truly being observed. The story of 3I Atlas has consistently been framed as an encounter, a visitor from another star system, an object of unknown origin. But perhaps it was never solely about the visitor. Perhaps the true significance of the event was our own reflection, how we react when confronted by what fundamentally does not fit our existing frameworks. Science articulates itself through spectra, wavelengths, absorption lines, and chemical ratios. Yet behind each precise measurement lies an emotional geometry, the intricate shape of human expectation. We examine this object as if it might confirm something fundamental about ourselves, our readiness, our imaginative capacity, our deep-seated fear of cosmic solitude. The phrase alien mirror is not about them, it is profoundly about us. Not they arrived, but we appeared in the very act of looking. The mirror of 3I Atlas did not reflect our faces, but our method, how we collectively decide what qualifies as natural, what counts as possible. It returned to us the same question quietly, hidden within every act of inquiry. What are we truly searching for? Light itself carries no preferences. It reflects every surface with an indifferent honesty. The luminous beam from 3i Atlas did not differentiate whether it originated from advanced technology or inert stone. It simply carried information, and we in turn transformed that information into a story. Perhaps this is the true meaning of alien, not merely other life, but other comprehension, a way of seeing that compels us to fundamentally reconsider the limits of our own. Every hypothesis formulated about its propulsion, every spectrum meticulously interpreted, is also a subtle portrait of the mind that conceived it. To gaze upon an object from another star is to confront the mirror of our own civilization. We are testing not just what we know, but how we know. If we ultimately find intelligence, we meet it as a reflection of our own. If we find only silence, that silence is still profoundly shaped like us. Because the mirror does not lie, it simply waits for the next gaze to arrive. And in its patient surface, we are always the ones revealed. Matter has never been as passive as we once believed. Even the simplest particle responds, adjusts, and aligns itself within a field. Every atom carries a faint trace of decision, not conscious, but patterned like a quiet rehearsal of choice, intrinsically embedded within physical law. So when we speak of 3i Atlas, accelerating without visible exhaust changing colour against the very grain of thermodynamics, the question naturally arises. Is there intention embedded within matter itself? Not intelligence as we typically understand it, but a structure of response so exquisitely refined that it mimics volition. Science describes the universe through a clear sequence of cause and effect, force, motion, reaction. Yet the data from 3i Atlas strains this fundamental sequence acceleration, without visible venting temperature shifts, without corresponding emission and behaviour that strongly suggest direction, yet with no apparent agent to direct it. In such profound contradictions, speculation becomes a valuable tool, not a weakness. Imagine for a moment that physical systems might contain a latent syntax, a subtle way the universe speaks to itself through the dynamic shaping of energy. Could 3i Atlas be an instance of matter briefly acting as a message, a vessel designed not simply to travel but to demonstrate a principle? If the non-gravitational thrust is not a mere accident of outgassing, then its internal structure must store and release energy in controlled intervals. This implies regulation, and regulation in turn implies logic. Whether that logic is born of biology, computation, or something beyond both becomes less critical than the profound recognition that motion itself can intrinsically encode purpose. Perhaps intention is not precisely the right word. Perhaps the universe has always been performing a unique kind of thought experiment, utilizing mass and momentum as the very grammar of its own awareness. The movement of 3i Atlas, then, is not a will pitted against inertia, but rather information elegantly translated into trajectory. From our limited vantage point, we label such coherence as mystery, but in another broader frame of reference, it might simply be physics extended to its philosophical edge, where every equation implicitly suggests agency, and every particle actively participates in a conversation too subtle for human language. To consider that matter itself might think, not metaphorically, but materially, is to stand at the profound threshold between science and wonder. In the faint blue arc of 3i Atlas, we glimpse not an alien will, but the astonishing possibility that intention itself is an inherent property of the cosmos. Every language in its origin begins with the naming of what shines. Long before complex equations, before sophisticated instruments, humans named the sky, not to possess it, but to find their belonging within it. Light was the first fundamental boundary we recognized, the luminous edge where the visible meets the utterly unknowable. Now, as we study 3i Atlas, we are once again drawn to that very same frontier. Spectra wavelengths, photon counts, all are meticulous attempts to articulate the name of light, using the precise grammar of scientific measurement. Yet no single instrument can ever capture its full encompassing meaning, because light is simultaneously both the message and the medium, the profound question and its own inherent answer. When the meticulously collected data returns from the James Webb Space Telescope, it will not arrive as eloquent sentences, but as precise numbers, intensity over time, position ratios, spectral indices. Still deeply hidden within those numbers, there resides a quiet, resonant syllable of recognition, a signature that whispers, "I was here and I saw you." Perhaps that is ultimately what we seek, not definitive proof of origin, but a profound communion achieved through illumination. To give light a name is to declare kinship, to acknowledge that what we observe is in a reciprocal sense also observing us, that photons traversing hundreds of millions of miles are not strangers, but rather a form of correspondence. The ancient astronomers spoke of lux, a word meaning both brightness and knowledge. To them, light was not merely a phenomenon, but a cosmic mind, the very instrument of revelation. Modern science, in all its precision, has not truly abandoned that deep-seated belief. We have only translated it into the rigorous language of equations. If 3i Atlas is indeed artificial, then its light constitutes a language, a deliberate composition, articulated across vast distance and time. If it is entirely natural, then that same light still carries profound meaning, because meaning is not externally assigned. It spontaneously emerges wherever human perception encounters a discernible pattern. So we arrive at the profound threshold of naming, not to merely label but to listen, not to strictly define but to profoundly recognize. For every act of observation is an invocation, and every single photon received is in a sense a word returning home. In this deeper understanding, the name of light is not something we invent. It is something we remember each time we lift our gaze to the heavens, and as 3i Atlas gradually fades into the outer darkness, its enigmatic radiance remains a question still softly glowing, patiently awaiting the next observer to articulate its full significance. Every precise observation begins in a clean room, a space where dust, warmth, and even human breath are meticulously controlled, where particles are quantified by their very absence. But there exists another clean room, one that no physical filter can ever create, the chamber of thought itself. To truly perceive 3i Atlas with clarity, one must prepare not only the optical instruments but also the discerning mind. In astronomy, contamination is not merely physical, it is deeply cognitive. Assumptions settle like invisible grains of dust, fixed beliefs about what a comet should be, ingrained expectations of what an anomaly must imply. Each fragment of certainty subtly clouds the lens of understanding. Within a literal clean room, air circulates in a laminar, steady, purified flow. In the mental equivalent, attention must flow in precisely the same manner, no turbulence, no distracting noise of desire, only pure, unadulterated observation. Is the profound state scientists strive to achieve before any critical measurement, a mental vacuum stripped of all preconceived conclusions, receptive only to the incoming light. Imagine standing beside a telescope dome just before dawn. The temperature outside slowly equalizes, the massive mirrors gradually cool, your breath leaves no visible trace in the crisp air. The intricate machinery hums rhythmically in perfect synchrony with your pulse. What you are meticulously preparing is not solely an instrument, but a profound condition of awareness. You're consciously aligning your inner atmosphere with the vastness of outer space. This too is a fundamental methodology. To think with absolute clarity is as vitally important as calibrating a highly sensitive detector. A single bias can irrevocably skew an entire dataset, just as a single mote of dust can scatter a delicate beam of light. The James Webb and Hubble space telescopes operate within meticulously controlled vacuums, their senses shielded from the disruptive heat and radiation of the cosmos. Human inquiry demands this same rigorous discipline, a vacuum of assumption, a shielding from the heat of ingrained belief. When 3i Atlas was initially analysed, many scientists prematurely dismissed its strange characteristics as mere data error. Others, with equal haste, rushed to label it as an alien craft. Both reactions in their own way contaminate the mental cleanroom. Between these two extremes lies the profound posture of true seeing, neither outright denial nor unbridled fascination, but a neutral, open receptivity in which the phenomenon itself is allowed to define its own nature. To observe in such purity is not detachment, it is in its deepest sense an act of devotion, because clarity is fundamentally a form of care. In that stillness, both the sophisticated telescope and the human mind serve the exact same overarching purpose: to allow the universe to reveal itself without any human interference. And so the crucial first step toward truly understanding 3i Atlas is to meticulously clean the space within our own perception until thought, much like a perfectly polished lens, becomes utterly transparent to the incoming light. Numbers arrive without inherent emotion. They settle into memory like cold, precise rain magnitudes flux, ratios, albedo curves, each exquisitely exact, each utterly indifferent. Yet somewhere between those cold digits and the receptive mind, meaning slowly begins to take shape. For 3i Atlas, the data is pure spectral bands meticulously recorded across ultraviolet, visible infrared and radio wavelengths. Each measurement returns values exact to 6 decimal places. Temperature, gradients, angular momentum, color, indices, all of them whisper what happened, but they remain silent on the question of why. The profound question of meaning does not reside within the photon itself. It lives in the intricate space where human perception interprets discernible patterns. Science formally calls that process inference, but in its deeper, more contemplative sense, it is contemplation. To transform raw data into profound knowledge, we must undertake a delicate translation from sheer quantity into meaningful relation, from precise measurement into profound understanding. It is a slow, intricate alchemy where the very act of reading becomes a heightened act of awareness. Each scientist seated at their console engages in this same inner ritual. They trace meticulous lines on a graph, carefully correct for noise and calculate residuals. And in that repetitive devotion, a quiet realization gradually forms that behind the meticulous order of numbers lies an intelligence not separate from us, but beautifully mirrored through our own inherent logic. Meaning then is not merely extracted from the universe, it is co-created with it. The photon records the event, the observer completes the sentence. Data is in essence half a conversation patiently awaiting a reply. In this illuminating light, 3R, Atlas ceases to be merely an object of detached study. It transforms into an interlocutor, a profound opportunity for a dialogue between mind and matter. Its improbable acceleration, its profound silence, its impossible blue. These are all lines in a cosmic script that invites deep comprehension without necessarily offering an immediate conclusion. What ultimately remains is not absolute certainty, but a profound sense of coherence. We recognize patterns not because the universe insists upon them, but because human awareness and the cosmos itself share the same fundamental geometry. So the work of transforming raw data into profound meaning is not about solving a simplistic riddle, but about listening more precisely, about allowing numbers to speak in their own inherent rhythm until they reveal what they have always contained, not explicit messages from beyond, but compelling evidence that understanding itself is a fundamental cosmic process. And when that profound realization settles, science and wonder seamlessly meet not as opposing forces, but as inseparable partners in the same grand sentence the universe has been writing since the very first light. There are 2 fundamental ways of seeing. One measures, the other listens. One meticulously builds equations, the other patiently waits. Between them stretches the quiet, boundless field where profound knowledge and exhilarating wonder converge. Through the enigmatic presence of 3i Atlas, those 2 distinct lenses have come into sharp focus. Instruments meticulously recorded acceleration without visible exhaust color, without a corresponding source of heat and motion, without any discernible cause. Silence in turn recorded something even more profound, that reality often conceals its deepest truths most effectively when it steadfastly refuses conventional explanation. And when the analytic mind and the contemplative spirit seamlessly overlap, the image of understanding finally clears. To gaze through the scientific lens is to ask, how does this fundamentally happen? To look through the inward reflective lens is to ask, why does it move us so profoundly? Neither question taken in isolation is complete. Only together can perception truly blossom into profound understanding. A single photon departs a distant unknown surface, traverses vast cosmic dust, and magnetic winds, passes through the chilling cold of 1 billion unlit miles, and finally encounters a mirror meticulously polished by human hands. We can precisely trace that path using mathematics energy, divided by Planck's constant frequency, multiplied by speed arrival time measured to the microsecond. Yet none of that intricate calculation truly describes the sacred moment the photon becomes perception, the instant when a cold number transforms into a deeply felt emotion, when light itself blossoms into conscious awareness. That is the profound point where the 2 lenses seamlessly meet. The physicist diligently records, the observer deeply reflects. Both actions in their own way complete the same grand circle, the universe witnessing itself through the intricate tapestry of consciousness. For a fleeting heartbeat, rigorous measurement and profound meaning dissolve into a unified whole. Atlas now drifts outward, beyond the ever-decreasing sensitivity of our current instruments and senses. Its long orbit extends deep into the interstellar dark. Its enigmatic glow gradually thins to the very edge of human perception. but indelible traces remain meticulously archived spectra, precisely plotted trajectories, and the haunting memory of that impossible blue. It lingers as both undeniable evidence and potent symbol raw data, and a profound dream captured within the same line of code. Perhaps this is the universe's subtle way of teaching humility, not with thunderous pronouncements, but with exquisite precision, by presenting forms that exceed our current definitions just enough to gently stretch the boundaries of our comprehension. Every encountered unknown becomes a gentle, profound instruction in perspective. We meet the unexplainable, and it subtly adjusts the focus of what it truly means to know. Knowledge too orbits. It departs the comfortable certainty of the familiar, sweeps daringly close to profound mystery, and ultimately returns subtly yet profoundly altered. We do not conquer the unknown, rather we patiently circle it until our very instruments transform into questions themselves. Each new question reshapes the questioner. That is the true exhilarating velocity of understanding. Light itself is the ultimate instructor. It never truly stops, it only continuously changes form. It departs one distant star, traverses the vast void, enters matter, nerve and thought, and ultimately culminates as profound comprehension, only to begin its cycle anew. This endless intricate translation is the very pulse of being raw energy becoming conscious awareness, and that awareness in turn returning as insatiable curiosity. Every observation continues this same eternal cycle. Data leaves its source, travels through immense distance, meets focused attention, and finally blossoms into nuanced interpretation. Meaning, much like starlight, is never born from absolute nothingness. It is the persistent echo of what already exists, patiently revealed by the passage of time and the cultivation of profound patience. There is in fact a rich spectrum to silence itself. The first kind is the overwhelming silence of distant space, so vast and immense that light itself eventually becomes faint and almost imperceptible. The second is the disciplined silence of restraint, the conscious choice to listen deeply and comprehensively before prematurely concluding. The last and perhaps most profound is the resonant silence that follows deep comprehension, when there is genuinely nothing left to add, because the truth has at last completed its sentence. Those who diligently tracked 3i Atlas once feared this silence signified profound ignorance, but in the years that have since passed it feels much more like an open invitation, a pause long enough for the human mind to meticulously equalize with the vast complex reality it seeks to understand. In that profound pause, knowledge truly breathes. The universe speaks most clearly, most profoundly when we finally cease our strenuous attempts to translate it into our own limited terms. So the observation ultimately concludes not with a definitive answer, but with a new deeper discipline of presence. To know is to witness. To witness is to seamlessly join what is known. Every photon meticulously recorded, every hypothesis painstakingly refined, is in essence a mirror subtly turned inward, compelling proof that consciousness itself is an intrinsic part of the scientific method. We are not external to the experiment, we are in fact extensions of it. Two essential lenses remain the scientific, precise, quantitative, sharp as geometry, and the contemplative, wide, soft, patient as the boundless night. Used in harmonious conjunction, they transform rigorous analysis into a profound communion. One measures the intricate architecture of reality, the other measures the profound silence that holds it all together. And somewhere in the sacred space between them, meaning slowly takes tangible form. Now close the instruments, allow the whirring fans to still let the data streams pause, the intricate graphs flatten to a serene calm. Step outside the control room, take a deep breath into the same ancient air that quietly carries the starlight from across the cosmos. Above you, the sky is not distant and remote. It is profoundly reciprocal. Every single point of light subtly returns your gaze. You are an integral part of the vast network of cosmic attention, a vital node in the universe's own ongoing act of self-awareness. When you gaze upward, you complete a circuit that began billions of years ago. The light that softly touches your eyes is ancient beyond comprehension, but the profound act of receiving it is entirely new, entirely now. That is precisely how the cosmos perpetually renews itself through the infinite process of perception. We are not merely passive observers, we are active continuations. Our eyes, our instruments, our insatiable curiosity, They are in essence the universe itself reflecting upon its own profound existence. Every discovery is a moment of deep remembrance, every measurement a heartfelt confession of boundless wonder. A question remains soft and profoundly sufficient. What if discovery is not about finding something entirely new, but about deeply remembering what the universe has always intrinsically known about itself? That question does not demand an immediate answer. It asks for a profound stillness. And in that stillness, the two lenses science and wonder seamlessly merge. Light eventually fades. Silence, however, remains. We stay awake within its profound embrace. The universe does not in its ultimate reality end in darkness. It ends in profound recognition, and in that ultimate remembering, we ourselves become the very light that gazes back, and that quietly is profoundly enough.